Do you guys have any questions on anything before we get started? Let me make sure that I'm covering everything before tomorrow's lab. I think I am. I'm gonna cover all these so you are able to do the lab tomorrow. So basically we are going to cover the operation of the NMOS and PMOSes, the two fundamental devices being used for the modern integrated circuits. So NMOS, PMOS, that's why it's called complementary MOS, right? It's a CMOS. You'll see that our textbook has a very big text in the middle. It's CMOS. It's complementary MOS. Why it's called complementary? Because many years ago there's no PMOS, it's just NMOS, and the very old, even the CPUs being used for very old computers, these could be just NMOS logic. So the way to do that is you have a NMOS here and a pull-up resistor on the top, and you can still form logic. Why is that? Because this is like 10K resistor is pulling this pin up. So this is V out and the V in. Okay? So if you don't turn on the channel of the transistor here, V out to the ground is disconnected. So V out will be put up to ground. So you are getting a 1. So which means if you have V in to be 0, like 0 volts or ground, it's not turning on this guy and you're getting a 1. If you turn this on, you give a 1 to V in, this channel is on, so V out is shorted to ground through this channel of the transistor, and you are getting a 0. So I can use a switch, it's just being used as a switch and a pull-up resistor to form logic at the output. But definitely this is not ideal because first, the resistors are dissipating a lot of power, right? And another one is resistor takes a lot of space. If you're thinking about using NWL resistors, they are maybe 100 micron in length. But nowadays, the PMOS, a little PMOS on the top, is probably only 5 nanometers as the smallest one. So you just use a PMOS and NMOS as a complementary two devices, one on the top to pull up the pin to VDD, another one NMOS at the bottom to pull everything to pull it down to ground. To form a very basic logic gate. So this is actually an inverter, and you can form all different kinds of logic gates by using PMOS and NMOSes. So it's the modern structure of the circuits, even for the 5, even 2 nanometer technologies, it's still not changing. It was invented, I don't know, 30, 40 years ago, but now it's still being used for the latest node from TSMC, even 2 nanometers. It's just a transistor structure and number of metal layers are being changed. And the smallest channel length is being changed, but all the rest are still the same. The logic gates are still logic gates. So you learn whatever here from the textbook is actually being used in the industry, in your modern devices. So now let's talk about how this works. I mean, we draw the picture is easy. We know that this is an inverter, but how that works. So the fundamental device or operation comes from the NMOS transistor. Let's look at the cross-sectional view of the NMOS first. So we covered this a little bit on Friday, but I'm going to repeat this one more time and make sure everybody can get it. I'm not expecting anyone can master this from one shot. So remember we have a wafer here, right? And we have a gate. If it's NMOS, it's going to be N plus here. It's heavily doped N-type material. And this is a P substrate. Okay, and we talk about that from Friday. The P sub needs to be shorted to where all the time? Ground. Keep that in mind. Okay. And we doped a little P plus within the P sub, and this is called what? In general, this is a well tap. Great. Because the P plus is being put in the P sub is actually making a short circuit. And this is called a P tap because it's a P type well type, or you can say P dash tap. And this need to be shorted to ground because of what? To avoid what? The body effect. This is VGS. This is source terminal. This is the drain terminal. This is a gate terminal. And VGS, turn it on, so it's attracting a lot of electrons to form an electron channel here, right? And then you apply a force, which is a DC voltage potential through the channel, which is called VDS, drain, source, gate. So it's providing the pressure which is able to flow electrons within the channel. So, you know, apply a voltage is easy, but how do we determine how much voltage we want to apply to the terminals? How much? So this is determined by which region you want to operate your transistor in. Yeah, so there are three different, is that three? Four different regions. And the three different regions. The third region is not being used because it's called cutoff. So what's happening is, I'm going to draw a couple pictures over here. So if you look at the notes, the handout I gave to you guys, right? And on the top right corner, the four figures shows all the status of the channel. The resolution is a bit low here, but I'm going to draw it on my notes for you guys. If you look at the first one is actually a no VDS, right? So if there's no VDS, okay, just apply a VGS. Okay, and this voltage is going to attract electrons from the substrate to here and form a layer of channel, and it's should be even and it's flat at the bottom, and there's no triangle shape channel at all because there's no voltage potential applied to the two terminals. It's just a universal electron layer or channel over here. So the second one, I think it's the one on the right hand side. It's probably not really accurate here. I mean, so all these, I mean, just look at the notes, not exactly on the handout. And the next one is that if you apply a voltage here is still VS, for example, it's shorted, and here's VGS. This is VDS. And you can tell that this is symmetrical, right? So you cannot really tell differences between drain and source. Especially the C5 technology, it's actually equivalent. You know, it depends on where you apply the higher voltage and where you ground it. So if you ground it over here, this is considered as source. This is considered as drain. Okay, but now by looking at this figure, okay, whenever we apply the little VDS over here, what's going to happen is the shape of the channel will look like this. It's going so this side is moving up. Why is that? It's because if you just look at the voltage difference between gate and drain, it's actually getting smaller because the voltage here is getting higher, and the gate voltage is not changing. So even though I label this guy the VGS, is because the voltage source here is grounded, and also the source terminal is also grounded. So VGS is basically the gate to source voltage difference. It's basically the gate voltage. So VG equals VGS in this case. So if you look at the voltage difference between G and S, it's pretty big, right? So if it's pretty big, it's not really reducing the... So if you have a bigger voltage difference between these two terminals, you can imagine there's a stronger electric field. So it's actually getting a thicker channel over here, electron channel over here. And for this terminal, because you have a higher voltage here, so it's actually reducing the depth of the electron channel. So it moves up a little bit. So the thing is, because you still have a channel, electron channel, connecting channel to this terminal. So when you have a higher voltage of VDS, if you increase VDS, the resistance of the channel is not really changing too much. Why? Because you still have a contact. You know, the electron channel is still make a contact to the terminal. But the thing is, it's still shrinking. Whenever it's shrinking, you got less amount of electrons. So you are increasing the voltage here. Ideally, it shouldn't change anything. If the resistance is not changing, you are not really changing the resistance. It's just that the current will go up, will keep go up. So you can imagine if V is going up and R is not changing, so I will go up. That makes sense, right? It's going to be linear. So what's happening is at the very beginning, when this is VDS, for example, and this is IDS. So IDS is a current flowing from D to S. It's a current, channel current flowing that way. So if you increase VDS at the very beginning, ideally it should be linear, but whenever it's keep going up, if you keep increasing VDS, this resistance is getting more and more higher resistance introduced to the channel, and you are actually bending that current curve. It won't be that straight. Will go this way. You agree with that? Because you got higher resistance. It's not keep going up anymore. It's gonna, turn a little bit. Whenever it reaches this point, so when you increase VDS to a certain value, it reaches this point. So the electron channel reaches this corner. Yeah, these are the electrons. And this state is called pinch off. And if you keep increasing VDS, you are going to have this line keep moving to the left, and there won't be any contact between the electron channel to this drain terminal. So right before that, this state is called pinch off. So the voltage over here at pinch off, VDS equals VGS minus VTHN. THN is threshold voltage of the NMOS transistor. Let me write it down on the paper. So VGS has to be larger than VTHN in order to turn on the transistor. So it's actually VGS has to be larger than this voltage in order to form a decent depth of the channel to make sure there's you can turn it on. Whenever you apply a VDS, there will be a decent amount of current flowing through the channel, so you are turning it on. So you have to apply a VGS which is larger than this first. So here's the parameter is given from the process. Nobody can change it. Depending on the C5 technology we are using, VTHN equals 0.8 volts. So VGS has to be larger than 0.8 volts in order to be considered as it's being turned on. The NMOS is being turned on. Okay. So look at this point here. When I come back to this VDS to IDS is the IV curve. So VDS on the x-axis has to be larger than VGS minus VTHN in order to move. In order to reach pinch off, and then you keep increasing VDS, what's going to happen is ideally, this will be flat. You will see on the textbook, it's shown that this is totally flat, but in the real world, this won't be totally flat. It's going to go up a little bit, but not too much. But we consider that it's flat. Okay, it's going to be flat. So why that? Why after pinch off it's getting flat? So there's a note. The first paragraph on the handout paper actually explains it. Now let's talk about this really quick. So after pinch off, for example, it moves to this direction. You keep increasing VDS. Here's VGS. S is grounded. Okay, keep increasing VDS. So the thing is, this is not changing. Usually the gate voltage is 5 volts, just the VDD, right? It's not changing. And if you keep increasing this guy, whenever it reaches we're getting closer and closer to 5 volts. So the voltage difference between these two voltage terminals are getting smaller, and it's not able to really, it's called inverse the channel here. So it's not actually attracting much electrons to here to form a channel. But the VGS here is not changing. It still has a strong voltage difference to form an electric field. So you are still getting a pretty good depth over here for the electron channel. But the thing is, it's going to start moving towards this direction after pinch off. So after pinch off, the thing is, ideally it's getting flat. And why? You're probably wondering, hey, we don't even have an electron channel here. Why we are still getting current? It's getting flat doesn't mean we're not getting current. If you look at the y-axis, we're still getting a pretty decent amount of current flowing, right? Why? So basically, if you look at the curve, it's actually when you keep increasing, think about here. This is like 2 terminals, right? We keep increasing the pressure of the voltage pressure at the 2 terminals. I mean, based on your experience in the past, like according to Ohm's law, if you keep increasing voltage, we should get higher current, right? But in this case, it's not getting higher current, ideally. It's flat. So increase, after pinch off, it keep increasing VDS, you're not getting more current. Why is that? Because whenever this one keep moving to the left, right, you increase, yes, you do increase the pressure between the 2 terminals, but the thing is, you're also introducing more in resistance. Okay, or it's like getting it's being off. So the increase of the voltage pressure between the 2 terminals is being offset by the reduction of the available channel here. Okay, or you can say it's being offset by the reduction of the expansion of the depletion region. So this is the depletion region. Because there's no actual free particles, electrons or holes. For this case, it's electrons. There's no free electrons. It's all gone. So that's why it's called the depletion region. And the depletion region is expanding. Okay, so it's trying to introduce more resistance. And even though you increase the pressure between the 2 terminals, it's not getting significant increase on the current as a result. And that's called the saturation region. For all the modern digital devices, we all operate the digital saturation whenever, if you draw it here. So this is, because the current got saturated. And this region is called linear. And if you don't apply enough VGS, the curve is going to look like this. If you apply a smaller VGS, you got a curve like this. So it saturates at a different level, but still saturates and still shows a similar IV curve, depending on how much VGS you are giving to the gate. It could give 5 volts, but the threshold voltage is 0.8 volts. Could you give 3 volts to the gate? VGS 3 volts, would that work? Yes, it's going to show a curve like that. So this is VGS. You can also do this. This is VGS 1, VGS 2, VGS 3, VGS 4. So definitely VGS 1 larger than VGS 2, larger than VGS 3, larger than VGS 4 in this case. Okay, if the VGS for VGS 4 is probably 0.7 volts, so it's less than VTHN, threshold voltage of the NMOS, which is 0.8 volts. And this region specifically here is called cutoff. It's a cutoff region because it's not on. You cannot use it. There will be some leakage of current going through the drain and source, but it's not really effective. People are not operating that in that mode. So you have linear mode, saturation mode, and cutoff mode. Any questions on this by far? No. Any questions there? Anything? So it's very simple because it's just like a user manual, right? So people invented 50, 60 years ago and hand you that device. Okay, we have this device available and we can use it from the toolbox. So now it's just telling you how to use it. Just a user manual, easy. For if you look at from a different angle, for example, we keep VDS like 5 volts. And we sweep VGS from 0 to 5 volts. And now we are looking at IDS. So now it's changing because we're not really changing VDS. Like here, we're not changing VGS. If you just look at one of the curves, right? So VGS, whenever VGS is fixed, we're not changing it. We just keep changing VDS on the x-axis and looking at the IDS. So now we are doing it differently. So we x-axis becomes VGS, and this is still IDS, this is the channel current. So we keep VDS as a constant, like 5 volts. Right? So when VGS is increasing, what's happening is you are getting a current like this. And this voltage here is the VTHN. So this is where you can see VTHN, because VGS has to be larger than VTHN, and you can consider this is on, right? So after this voltage for the VGS, 0.8 volts, and the transistor is on, the current is increasing exponentially. So this is 1 VDS, like VDS1. You fixed it, like 5 volts. So if you increase VDS1, how do you plot that curve compared to this guy? On the left, on the right. Higher VDS will be on the left or on the right compared to this existing one? Left. Why? Let's see. Because the same VGS, this is giving you more current. Okay? So actually this, if this is VDS1, this is VDS2, so this is larger than that. Make sense? And we're going to plot these curves and these curves during the lab and also on the quiz today as well. Just plot it. You don't have to just give a very simple labels. Any questions on this by far before we do the quiz? I mean, we still have 10 minutes, 15 minutes before the quiz. Any questions on this?
Can we go over what was on the right side again?
The right side?
Yeah.
Here?
Yeah, or left side, sorry.
Is it left side?
Mm-hmm.
Yeah, so for this one, why VDS is larger than VDS1?
Yeah.
Because the same VGS, you just turn on, it's like, this is like a valve. The valve of the faucet, right? You turn it on, turn like 5 turns, so you have a certain VGS equals 5 turns. So you open up the channel to a certain width, right? And then now you start giving a pressure from one side to the other side of the faucet. Same VGS, same number of turns, higher pressure will give you a higher current. Does that make sense?
Yeah.
Okay, this is IDS 2, this is IDS 1.
Wait, wouldn't eventually those would eventually flatten out, right? If like
No, it's not. It's keep increasing. Oh, it will eventually.
Yeah.
It's like this.
Yeah.
Yeah.
Okay.
Yeah. But we don't really look at that part. It's probably close to getting damaged. Yeah, we just look at. So keep in mind, basically, so everybody should know that because this is super fundamental. I'm not covering anything extra here, right? So whenever people asking you should have these 2 images in your mind. That's why I'm putting this on the quiz. You know, give you more like alert, right? You need to know this right away. So 2 images, VGS versus IDS and VDS versus IDS. Okay? Even though you don't know why the VGS versus IDS looks like this and VDS versus IDS looks like this, right? You know, so it just works that way. It's a device given to you and it's a user manual. You just have to know it works that way. Okay? So they are being governed by the physics, some of the equations, the physics or quantum mechanics, but this is not what we're talking about here, since there are so many other things to know, right? So VGS versus IDS, you are expecting an exponential curve, and you expect a VTHN. It has to pass VTHN to get that increase. That's VGS. That's the valve of the faucet. Okay? See, here's the valve. It looks really like a faucet valve, right? Here, you turn it on, give a turn, several turns, and you turn on the channel. And then you give a pressure, the water starts flowing down. Make sense? Okay. So that's VGS versus IDS. IDS is the current flowing through it. Why we always care about IDS? I mean, in analog, IDS determines a lot of things, like a gain and a resistance to the channel and a lot of things. So for in digital, IDS determines the driving capability. If you have more current flowing through it, you can charge and discharge the flowing circuit more efficiently. Okay? So more current equals more driving capability for the digital circuits. So a lot of times it's a trade-off. If you make the channel bigger, make the device bigger, you can definitely flow more current into it, but it's also taking a lot of space. Can you remember that? VGS versus IDS is like, pfft, that's probably why.
I guess from like a logic perspective, what would be like your constant input and what would be like your tolerable input? Like, so your gate would be your constant 5 volt power, and then like your drain would be the logic input that you're putting into the system.
Yeah.
Okay.
Yes.
Sorry, I didn't know if I was interpreting that.
I think that's a very reasonable explanation.
Okay.
So if you look at the VDS to IDS curve, you are having these ones,
Yeah.
right? There's VDS versus IDS, linear. First, why is it called linear? Because it looks like a resistor.
Yeah.
You got a V, delta V divided by delta I are getting pretty much constant value over here. It's like a linear
Yeah.
thing. So the question is this region having higher resistance or this region has higher resistance?
No, the saturation.
Saturation has higher resistance because you're increasing voltage is not changing the current. It's like a super high resistor. Okay? So whenever it's being operated in the saturation region, it's being considered as a current source. So that's why a lot of people are using transistors as a model of voltage control current source. Why? Because you increase the voltage, you are increasing the current source output current. Right?
So
Questions?
on the other graph,
Yeah.
when you in
Mm-hmm.
the gate to source voltage,
Mm-hmm.
is that kind of pushing that channel back open so that you drew like the pinch off of the channel in between the in plus regions? Is it just pushing it back down?
This?
Yeah.
Yeah, so it's actually attracting. So it's because you have the electric field, this is still holding that electron channel here, layer here, so it's not disappearing because you have a difference, voltage difference here is forming an electric field. But here it's getting smaller because this is getting very close to it. It's almost so the electron field, the intensity of the voltage difference or the drop is getting smaller, so we are losing it. Right? Hard to imagine. It just works that way. So if whenever you have a smaller voltage, you definitely have got a weaker electric field. So you are losing that losing that electron layer here. And so this is a pinch. So this is after pinch off, and this is called pinched off. It's already pinched off. And also another thing I didn't cover here is the channel length now is this much. It's not this anymore. Okay, just keep that in mind. And this is called channel length modulation. There's a name for it, channel length. And we're going to introduce the current equation later, so I have to consider the delta L here. This is L, so this part is actually the delta L. It's affecting the current, the IDS eventually. So we have to introduce the delta L into the equation to get a more accurate result of the current. CLM, channel length modulation. Any question on this?
Yeah, so the graph where it's showing the plastic that one's a VGS
Mhm.
versus IDS,
Mhm.
and the other one's VDS versus
Yeah.
IDS.
Yeah.
Okay.
So things you need to know, right? So whenever enters saturation region, is that VDS has to be equal to VGS minus VTHN. It's hard to memorize, but I'll just let you guys look at the notes when you're doing the quiz. Right? Yeah, we used to do a closed book closed notes in the past, but now I think it's okay as long as you guys understand what's going on. So that's for NMOS, right? That's for NMOS. What about PMOS? Very similar, right? Very similar. So PMOSs are fabricated in N well. We covered this on Friday, so watch the video if you missed it. So PMOSs are being put in N well, and we need a little N plus over here, and this is called the N tap, right? N tap. To avoid body effect. And so this is source, this is drain, and we give a high voltage, positive voltage over here is called VSD, and here is called VSG. VSG is basically S to G voltage difference. You can draw it that way. You know, any questions on this?
Well, actually, isn't the direction of the voltage, did you flip that? Instead of doing from gate to source, you're doing from source to gate now?
Yeah, so gate to source becomes negative, so we probably prefer SG. So you can see from different textbooks. Sometimes they use VGS for PMOS as well, but it becomes negative. It's confusing people. So why? And so it's just getting flipped, but no other major differences. So the PMOS is from our technology we are using is VTHP is 0.9 volts. It's a bit higher than the NMOS threshold voltage. The reason for that is the mobility of the electrons are a little bit higher than the mobility of the holes. So that is why the threshold voltage here is a bit larger, because you need a more effort to turn it on, right? You know, PMOSs are attracting holes. They are forming a channel of holes, and the mobility of the holes are a little bit lower than mobility of the electrons. You know what I mean? So in that case, it's just more difficult to turn it on. So it's 0.1 volts difference over there, and for all the rest, it's pretty much the same. You apply a voltage here which is larger than VTHP, then you turn it on, form a channel of holes, and then you give a pressure from source to drain. It starts flowing current in that way. So actually the electrons going towards the opposite way, but you consider the holes are moving to the left. So this is called ISD. So from the lab, it could be a little bit different depending on the polarity of the voltages are looking at. You can see some of the curves are being plotted in the opposite way. If we click this one, you just need to know what's really going on over there. We can actually plot it in the normal way. It's just example was given, you know, in this way. It's really weird. The PMOS is, you can see it's plotting, it's from -5 to 0. So it's actually, you know, that's a VDS. Wait, I don't really care. It's just the curves are, the shapes looks correct. If you get this, it's okay. So you can modify the spice code of the PMOS in order to get the curves that we are used to, which is fine. If you see this, it's okay. It's definitely okay. But usually we don't plot it that way. And you can see it's IS. So it's very interesting that the transistors, let me see. So transistors, if you You could definitely add a minus sign in front of it to flip it. But for LT Spice, there's a default direction of the current. If you're plotting VS, it shows this. If you plot VD, it's probably, I think it's measuring the current flow into S or into D. You know what I mean? So if you're plotting IS, like this guy, if you, for example, you get it done, and you right click, add a trace, plotting trace from LT Spice, right? If you are adding IS, it's plotting the current flowing into S. No matter which terminal you're plotting, it's plotting the current getting into it. That's how it's being designed. If you're plotting ID, it's actually plotting the current flowing into D. And you can see if you plot ID and IS, you are actually getting opposite directions of currents, but they are pretty much the same current. You know what I mean? So IS is a current getting into S. The ID is a current getting into ID. Just to let you know. I don't really care if it's like looks like this or looks the opposite way, as long as you're getting these curves, the saturation and linear and cutoff regions. It's gonna be fine. See this one. And sometimes if you don't specify the while connection or the body connection, you can have a force terminal of the device. And you can see you right click and there's the option, I think. It shows you how to do it, but we didn't have any problem in the past. So it just follows instructions and you can introduce the force terminal over here. And what is that force terminal? It's a body connection. So it's actually the well tap. It's a well tap. Okay? So by default, all the well taps of PMOSes are shorted to the highest potential of the circuit, and all the well taps of the NMOSes are shorted to ground. So given that, why do we still need this force connection? It's just by default, we just directly do it. So Electric VLSI as a software, it gives you two options. You could either go to the setup, there's a preference, the setup, you just ignore that force connection, and by default, you connect all the wells to either VDD or ground, okay? And if you don't want to do that, you want to customize some of the connections, you can display that force terminal and you have to manually connect it to either ground or VDD. Either way. So you can see this example here, we show this connection, and you have to make a connection to somewhere if you display this little body contact. And you can see for the NMOS, I short it to ground. Okay? So another question here, if I don't have this force terminal, do I need this ground in the circuit? I still need that. Otherwise, it's going to report errors. Because we are, by default, right, if you don't display this terminal, still keep in mind, all the NMOSes are still being fabricated in the PMOS. And the PMOS is, the P-sub. And the P-sub is still grounded. So you still need to grab a little ground symbol here, and you don't connect this to anywhere else. You just place this little ground symbol in the schematic, and that's it. And you are not connecting this to anywhere because you don't have the body connection for that version. You know, so all the VDD symbols and the ground symbols are served as global symbols, can go up and down in between different layers. I don't know if you understand that, what I'm saying here. So you don't have to export VDD and grounds. Like you build a little circuit, and you build another circuit to wrap it, and you build another layer to wrap it, right? So you export all the pins in order to make them visible at upper hierarchy, right? But for global power sources or symbols, you don't need to export them. So VDDs are always VDDs. You place the VDD symbol at the bottom layer, and you can directly use it at the top layer. They are being automatically exported to the top. Same for ground. So you can directly use VDD or ground. They are always universal global pins. Any questions on this? A very quick explanation to the SPICE code over here. This is called DC sweep. And for, as an electrical engineer, you do need to know SPICE really well. Super fundamental stuff. And DC sweep, AC analysis, and transient analysis. And what else? Yeah, let's just, oh, there's another one. Let's just stop here for now. So transient DC and AC. For transient analysis, is x-axis in the time domain. For DC sweep, the x-axis is actually voltage. There's no time. For AC analysis, the x-axis is frequency. And for the arguments for the DC analysis is VD. Okay, see VD. What is VD? VD is the drain voltage. It's just the one voltage node compared to ground. So VD is being swept from 0 to 5 volts. So you can imagine x-axis will be VD from 0 to 5. And it's 1 millivolts per plot. So 1 millivolts, I plot a dot for the plotting. And VG VG 0 to 5 and 1 volt. So what's happening over here is I'm trying to plot multiple curves. So even though I'm sweeping VDS, okay, remember the VDS curve? Like this, right? Whenever I'm sweeping VDS, I also want to add VGS into it. So how to add VGS into this curve, which is basically adding a little argument, a statement over here is VG from 0 to 5 and 1 volts per step. So it's going to plot 0, 1, 2, 3, 4, 5. 6 different steps into this curve. You are seeing VDS versus IDS, but also you are seeing 0 VGS, 1, 2, 3, 4, 5 VGS curves. So you are displaying multiple ones as well at the same time. And you can imagine that eventually you are plotting the, I didn't show the plotting, but it's going to be something like this with different VGS, and it's a VDS versus IDS. Any questions on this before we do the quiz? Any questions on the curves? I mean, the quiz is probably just take you 5 minutes, even 2 minutes. It's just plotting the curves, nothing else. I want to cover a little bit more here. So if I make a connection of the circuits like this, so here's the NMOS and the drain, here's the gate, here's the source. Given that VDS has to be larger than VGS minus VTHN, and this term we gave a name to it. It's called VDS, comma. Set as a saturation voltage of the VDS. So on the curve, VDS, IDS, like this, right? And this point is actually VDS set, which is VGS minus VTHN.
That's also the pinch-off point.
Pinch-off point, yes. Just keep in mind what happened. So if I short gate to drain, which means VDS equals VGS,
Yeah.
then what's going to happen?
We're gonna get the channel length modulation, right?
So if you look at this equation, okay? So if VDS equals VGS, and if you replace VGS with VDS, what's going to happen?
Oh, you get cut off because
No. So because this equals this, right? It's given, okay? And here's VGS. We can replace it with this, right? No problem.
Yeah.
It always works because this is 0.8 volts. The VDS is always larger than the VDS minus VTHN.
Yeah.
It's going to always work. Then what?
Oh, well then
It's always in saturation. So if you do this kind of connection, so you can guarantee